So till now we discussed that the thermodynamic states are nothing but pressure, volume, temperature, and entropy. Okay, now in this session we'll discuss with thermodynamic potentials. So what is meant by thermodynamic potentials are nothing but these are the energy functions combined, okay, of these variables like pressure, volume, temperature, and entropy. See, generally we are having thermodynamic potentials. Four are there. They are, first one, okay, is internal energy represented by letter U. Second one is Helmholtz function. Okay, so internal energy is U and Helmholtz function is F. Okay, and enthalpy represents capital letter H, and Gibbs function is G. These are the four, okay, thermodynamic potentials. Okay, that means, okay, these are the four thermodynamic potentials combining of these state variables. That means thermodynamic state variables. Now we'll discuss one by one. Before starting internal energy, first of all we should know these are the three formulas we should know. That is, first one is the first law of thermodynamics is nothing but dq is equal to du plus dw, and second law of thermodynamics is dq is equal to T into ds. Here dq is nothing but heat supplied to the system, du is internal energy, and dw is nothing but work done. And similarly dq is nothing but heat, T is nothing but temperature, and ds is nothing but change in entropy. And one more is we know formula dw is equal to pdv. So to solve the thermodynamic potential we should learn these three. So one is first law of thermodynamics and second law of thermodynamics, and dw is equal to pdv. So we should learn these three. Okay, now we'll discuss internal energy. Internal energy will represent letter U. Okay, so always remember, for example, if you consider any container, in this water or something liquid is there, when we supply heat to this container, what happens, these molecules having, okay, more kinetic energy. So that means they are moving in a random way. Okay, they are collide with vessels, okay, and molecules. Okay, so that always remember in this internal energy, okay, the processes due to the molecular constitutions and motion we are considering. That means here we consider both sum of kinetic energy as well as potential energy. Okay, the mutual attraction of these molecules you should consider here. So we know that first law of thermodynamics dq is equal to du plus dw. Okay, but we know second law of thermodynamics Tds, instead of dq we'll write Tds equal to, okay, du, and instead of dw we'll write pdv. Okay, so this is second law of thermodynamics, dq is equal to Tds, and du is as is we writing, and instead of dw we write pdv. Now we want internal energy, that means we want du. So du equal to Tds minus p into dv. Okay, but see, in this here only it should be, if you want to derive any energy function, it should be in only one variable, but here two variables are there. For that purpose, if you want to find a single variable, you have to do, okay, partial differentiation. Okay, so here with respect to S and V, so partial differentiation with respect to S and V, where S is nothing but entropy and V is nothing but volume. Okay, now see, for example, if you want to do partial differentiation with respect to S, okay, that means always remember here we will do with respect to first we'll do with entropy and then volume. Now first we'll do with entropy. So du by ds, or see, always remember dou or d both are same. Okay, little small change. Okay, here we are doing differentiation with respect to entropy, and we are doing constant volume. Now tell me, see, if you are doing with differentiation with entropy, so ds by ds value is 1, so t minus, and you see here volume is constant. That means if you want to do constant volume, okay, any derivation of any constant is 0, that means this term is 0. So therefore we'll get dou u by dou s at constant volume equal to t. Similarly, now see, till here we discussed with now entropy, with respect to entropy we did derivation. Now we'll do same thing, derivation. Now with respect to volume we'll do now. So that means dou u by dou v at constant entropy. Now see what happened to this equation. Now see what happened, derivative, okay, with respect to volume we are doing. So here s is constant, so constant differentiation is 0, and minus, so p into dv by dv is nothing but always remember 1. Okay, so therefore we'll get dou u by dou v at constant entropy equal to minus p. Now we already discussed that u is a perfect differential. Okay, that means always remember, if you want to do perfect differentiation, that means, okay, what happened, first of all we should consider d dou by dou v of dou u by dou s at constant volume is equal to dou by dou s of dou u by dou v at constant entropy. Okay, so that means always remember, for example, see here, if we consider dou u by dou s at constant volume is equal to, we got t. Okay, so that means we are doing this constant, whatever constant is there, that only. So dou v by dou v, okay, and same term we are writing here equal to, okay, here with respect to s we are doing differentiation, and the same term we are writing here. That means why we are writing like this, because of always remember it should be in a two variables. For that purpose, okay, we are writing this. But we know dou u by dou s at constant volume is equal to t. So therefore we'll write dou by dou v of t equal to dou by dou s of this one is nothing but minus p. So that means always remember dou t by dou v equal to minus dou p by dou s. Okay, so here what we are doing constant, with respect to entropy we are doing constant. So that means this is the relation with respect to entropy, and this is, okay, with respect to volume. Okay, so this is called first law, first thermodynamic potential. Okay, is nothing but internal energy equation. So in the same way, okay, we'll do for Helmholtz function. Okay ma, so all are same relations, same type only. Okay, now we'll derive Helmholtz function. So before that, okay, always remember, for deriving Helmholtz function also we have to consider the same relations, nothing but we know already, okay, we know already that is nothing but dq is equal to tds minus pdv. That only again I am here copying, du is equal to tds minus p into dv. Okay, So now in this Helmholtz function, we consider system undergo isothermal process. Okay, which process? Isothermal. So always remember in this isothermal process, okay, temperature remains constant. Okay, that means instead of T into ds, we will write T of, that means derivative d of Ts, because in this process, isothermal process, temperature is constant. That means instead of T into ds, we will write derivative of Ts. Now we will put instead of T into ds, we will write T of ds. Therefore the equation du equal to d of Ts minus P into dV. Now we transfer this term to that side, du minus d of Ts equal to minus P into dV. Now we will do differentiate, we will take common d. So therefore u minus Ts equal to minus P into dV. So let us consider this full term as Helmholtz function. Okay, let us consider this is an Helmholtz function. That means df equal to minus P into dV, where f equal to u minus Ts. Okay, this is called Helmholtz function. Always remember Helmholtz free function or energy function. Okay, now we consider this equation and we'll derive. Now see, f equal to u minus Ts. F is nothing but what? Helmholtz function. U is internal energy and T is temperature and S is entropy. Now we are differentiating on both sides. Okay, differentiating on both sides. Then df equal to d of u minus Ts. Okay, so now again we remove the bracket, then df equal to du minus d of Ts. So now we are differentiating on both sides. So df equal to d of u minus Ts. So df equal to, we remove the bracket, d into u du and d of Ts. Okay, now this is in the form of uv. Derivative of uv is nothing but u derivative of v plus v derivative of u. So therefore df as is we wrote, du as is we wrote, minus symbol, and this is in the form of uv. So u derivative of v plus v derivative of u. Now we remove the bracket, so therefore du and minus t into ds minus s into dt. Okay, so but we know that du is equal to already initially, initially we know that so du is equal to tds minus pdv. Instead of du we will write tds minus pdv. So therefore df equal to t into ds minus p into dv minus t into ds minus s into dt. Okay, so this plus and this minus cancel. Okay, so therefore we got df is equal to minus p into dv minus s into dt. Okay, but this energy is in the form of two variables. Now we want this single variable. For that we are doing partial differentiation. F with respect to V and T. V means volume and T means temperature. Same thing how we did for internal energy, same thing ma. So first we will do differentiation with respect to temperature as a constant. With respect to V first we will do. Okay, that means remember df by or dou V. Okay ma. With respect to temperature is a constant. if you do constant, temperature is constant, that means this differentiation of constant is 0. That means we will write minus P into dV by dV value is 1. Okay. Similarly, same equation again, dou F. Now this time we will do differentiation with respect to temperature at constant volume. So if constant volume, that constant now volume is nothing but this is 0. Okay, with respect to temperature we are doing, so dt by dt value is 1, so that we will get S is nothing but what? Entropy. Now again we will consider these two. Okay, so that means dou by dou t of this value we know minus P equal to dou by dou V of the full value, okay, we know that minus S. Okay, so therefore minus dou P by dou T equal to minus dou S by dou V. Minus minus cancel. Okay, so here dou P by dou T at constant volume equal to dou S by dou V at constant temperature. This is the called second thermodynamic relation or Helmholtz function relation. So enthalpy will represent letter H. So it is a function of internal energy and pressure and volume. Remember, in this enthalpy, this is nothing but isobaric process. Isobaric process, pressure is constant. Okay, so therefore we can return, differentiating on both sides, we'll write dH equal to du plus P of dV, because see here isobaric process, pressure is constant, that's why we write like this. And we are using UV method, same as it is dH and du, and this is nothing but derivative of UV. So U derivative of V plus V derivative of U. Okay, but we know du is equal to, so already we learn this in the first derivation also we learn this only. So du is equal to TdS minus PdV, same thing again we substitute here. So therefore dH equal to du is nothing but TdS minus P into dV plus P into dV plus V into dP. This and this cancel. So therefore we got dH is equal to T into ds plus V into dP. Again here also we got two variables, so we want to do single variable. For that again we will do take partial differentiation. Let's take partial differentiation with respect to entropy and pressure. For this equation, first we will do differentiation with respect to entropy. That means dou H by dou S. We are doing constant pressure. Then see with respect to differentiation, ds by ds value 1. So we got T. And this we are doing constant pressure now. So that means differentiation of constant is 0. That means this full term is 0. Similarly, we are doing same equation dou H by, now this time we are doing a differentiation with respect to pressure at constant entropy. Now see, if you have constant entropy, that means this term is constant, that constant derivation is 0. We got V into dP, but dP we are doing derivative, so dP 1, so we will get V. Okay. Now see, with respect to constant, that means dou by dou P of this as it is, will write dou H by dou S at constant P equal to, again this is entropy, so we are doing constant number, that means dou by dou S of, as it is this term will write dou H by dou P at constant entropy. But instead of this we will write T, and instead of this we will write V. So therefore dou by dou P of T equal to dou by dou S of V. So that means, remember, with respect to S we are doing, that means this is entropy is constant, here pressure is constant. So this is called second third Maxwell thermodynamic potential equation. Now this is the last one. Okay, Gibbs function. We represent letter capital G. Now for deriving this, okay, we have to use same relation, that is nothing but H equal to enthalpy equal to internal energy plus pressure into volume. Now we are doing differentiation, dH equal to du plus, okay, derivative of PV. That means, remember, in this we consider two systems. One is we in this Gibbs function we undergo both two process. One is isothermal as well as isobaric process. So for that purpose, okay, we are doing now again see dH equal to, now our aim is to calculate first first we calculate Gibbs function. So for that du plus, this is again derivative of that means nothing but P into derivative of V plus V into derivative of P. Okay, but we know internal energy du is equal to, already we know that internal energy is nothing but T ds minus P into dV, okay, plus P dV plus V into dP. This and this is cancelled. So dH is equal to T into ds, okay, plus V into dP. Okay, now till now we consider isobaric process. Now we consider isothermal process. Isothermal process, always remember temperature is also constant. And that means instead of here dH is equal to this one, as temperature is constant, T into Ts plus V into dP. Okay, remember here we consider which process? Isothermal process. Till here we considered isobaric. Now we consider here isothermal process. Remember, in Gibbs function there will be both two processes are undergo, that is nothing but isothermal process as well as isobaric process. Till now we discussed isobaric. Now this is isothermal. Now this one you can transfer to the side. That means dH minus d of Ts equal to V into dP. Now here we consider d is a common, d of H minus Ts equal to V into dP. This full term we consider as a capital G. That means dG equal to V into dP, where G is called Gibbs function. Okay, that means G is equal to H minus T into S. Okay, so this is called what Gibbs function. Okay, now we'll do differentiating on both sides. Okay, that means remember dG is equal to dH minus d of Ts. Okay, so dG equal to dH minus, again this is UV method, T into ds plus S into dt. So this we remove the bracket, then so dG equal to dH minus T into ds minus S into dt. Okay, but we know, so we know that dH is equal to TdS plus VdP. This is the enthalpy relation. Okay, dH equal to TdS plus VdP, that we substitute in this equation. So that means dG is equal to T into ds plus V into dP minus T into ds minus S into dt. This plus TdS minus TdS cancel. So therefore we got dG is equal to V into dP minus S into dt. See, now again we got two variables. Okay, so that's why again we do partial differentiation. So take, okay, partial differentiation, okay, on both sides. Okay, P and G. So therefore dou G by dou P at constant temperature equal to, remember, so we are doing constant temperature, that means derivative of constant is 0. the dp by dp value is 1, we got v. And similarly dou g by dou t at constant pressure, okay, you'll get minus s. Okay, so again the same process till now what we derived all equations, same process. Again we are doing with respect to t, see dou by dou t of the full term will write dou g by dou p at constant temperature, okay, equal to, here p is constant, so that means dou by dou p of dou g by dou t at constant p. Okay, so we know this full term is nothing but v, this full term is nothing but minus s. So therefore dou v by dou t at constant, okay, pressure equal to dou by dou p of, this one is minus s, we'll write minus before, and this at constant temperature. This is called fourth Maxwell equation, okay, or thermodynamic potential. Fourth Maxwell thermodynamic potential. Thank you for watching.